morning? Is it just like a few hours after you woke up? Or is it like an agreed upon time? What's that?
My point preference is morning.
Right. Because like when does morning start? Is it a sunrise?
1 minute after midnight.
1 minute after midnight? I would say that that's late night, right? Because you say open late night. You think like late night, like 4, 2, depending, you know? And then morning, I think is like 4, 6, 8, you know? Ready to present? Want to present up there? You want to present here? What do you want to do?
100%.
Okay, you're going to use my computer?
Yeah.
Okay. Okay, let me get out. We're going to let a few people arrive. And today we are doing chapter 6.1. Okay, so we finished 9. Is that correct? Okay, so now we're going to do linear algebra, which you love. You love linear algebra to start with, so that's a perfect set of chapters for David. Trinity, you online?
Yes, I'm right here.
Cool. So if anyone else shows up online, otherwise I'll just match you up with someone who's in person if that's okay.
Okay.
What?
Could have been online too, but I'll be your partner.
You have a question, Will?
On the content calendar, it says we're doing are we doing 9.4 and 9.5 today? I saw it was. Yeah, it's not 1.4 and 9.5, like we did those already.
Oh, that's just not copy and pasted. Look. Yeah, we're gonna have to double check what these numbers are because this is just this without it being switched. I was supposed to update those. I'll update those after David presents, and we'll have a look at the homework. Because 6.1. Okay. Yeah. Where is 6.1? Let's look. I think example 6.1 might be the one that we're supposed to look at today.
I think there's 2 of them. Better in the section I'm doing.
Yeah, so I believe the first homework problem that I like to assign for this one. So this example 6.2, I think is the one that Angeli will present. Whereas, yeah, the capacitor one here, exercise 6.5. This is one that I like to have folks do. So, yeah. And I want you to do 6.1. Okay. Why don't we start whenever you're ready, and I'll just present the whole screen here. Okay. So you should just be able to, scroll up and down, or you can click these ones here, or I can change the screen for you. Any questions before we get started?
Yeah, I was just remembering.
Great. Got burnt. Went to J tree.
Went to where?
J tree. Joshua tree.
How many dogs again?
5. 5. Yeah, I went to 1 spring training game and 4 normal games.
What, yeah.
I gave Alyssa and David some of my tickets. They're not even here.
It's because they're at a Dodgers game, or they're camping outside waiting for them.
Yeah, that would be a few days to wait because they're playing in Washington right now.
Different camping.
Camping, yeah. Okay, go for it.
All right. Hello, everyone. The topic we're going to be discussing is simultaneous linear equations. So a lot of this part of the chapter, or I should say, the discussion I'm going to be doing is based on matrices. So we've learned how to do matrices in linear algebra when we took it, some time ago. The first topic that we're going to be talking about is what was it again? Is solving a variable in a matrix form. So we understand that in a matrix, there's rows and there's columns. And this is basically how we solve such variables, such as in this example right here, we have W, X, Y, and Z. And they're equal to some sort of thing. So we have a matrix here, and this is equal to a vector. And this matrix is multiplied into a vector column that has its variables. What we typically like to do is sometimes we find the determinant and associate it with that value so we could solve it properly. In computational physics, however, we approach things a little bit differently. One of the topics that is introduced for the book is Gaussian elimination. And what this is where we go through the process and we follow through in creating something like a staircase. So either we have the lower bound or the upper bound, meaning that if you see right here, if you look at on the second page on the right, on page 217, on 6.9, you see how we have a staircase of ones, right? And then on the lower left part, we see a bunch of zeros. And on the upper bound, we see just some random numbers. And what this does is that this Gaussian elimination allows us to solve such matrices in an easier way so that we could associate them with their variables. When we try to find the determinant of some sort, we have to do such as like, subtracting from different rows or swapping different rows or even multiplying them. Yes, it's a nice way to do it because we understand and we're familiar with it, but it does take up a lot of time and there is always a chance that we make an error ourselves. Yes, well.
So even though it has parentheses, I remember in algebra, instead of having parentheses, there'd be like a line between the variables and the 4x4 matrix or whatever you have. That's not multiplication, right? The parentheses, like multiplying the 4x4 by the 4x1.
Yes, it's considered multiplication. It's basically the variable that's assigned to, right? Because if you remember when we took linear algebra, right? You multiply these in, and this is like the row of the row of W, X, Y, no, sorry. The columns W, X, Y, Z. If you remember how to like multiply matrices.
Okay.
And that's how they're assigned. Yeah, go ahead.
It would just be like getting a bunch of like values from, let's say, serial, and you getting like this much from this serial, this much from this serial. That's what the X is.
Yeah.
Is how many appears.
Yeah. Yeah, that's what's going by. So we like to say it too as like a n by x times x matrix because it could go beyond of how many numbers it goes by of the size. So one of the things that we go into is back substitution. So back substitution is we here. So suppose we have a set of equations. So this is our main goal. Try to get that little staircase of just ones. And then we have such numbers right here on our upper bound. And on the lower bound, it's just all zeros. We do that every time. So notice how anytime we work with that matrix that you just saw on the previous page, we write it out like this, right? Notice how this top equation has all these assigned variables, W, X, Y, and Z. And as it decreases, you have less variables, X, Y, and Z, Y, and Z, and then finally Z. Well, what's one thing that one may notice instantaneously? Since Z is the only component on the bottom part, Z is already solved for. So then what we could do is with the back substitution, we go backwards and substitute it over and over again until we solve everything that we need to do. From there, we have our value solved. So in this case, W is equal to 2, X is equal to -1, Y is equal to -2, and Z is equal to 1. So from there, we already have our value solved for. So now let's combine these two different concepts together. The Gaussian elimination with back substitution. So let's see. Sorry. Oh, excuse me, this is an example. Sorry, I didn't do that example specifically. Let's go into pivoting. So pivoting, is where, if you'll see here. Yes. So pivoting, if you see here, here's this first matrix that we have right here, and then this other matrix that we have here. What we refer to as pivoting is sometimes when we switch things around. So what I was mentioning before is that typically in linear algebra, we like to switch things around so that we can find a determinant. This is kind of a similar idea. Notice how in row and in 6.17, we have this first row, right? 0, 1, 4, 1. And the second row is 3, 4, -1, -1. Pivoting, what this allows us to do is it allows us to switch it. So we switch it, and notice how they're flipped now. And we could switch this in any kind of way, as long as we're aware of what kind of pivoting we are doing ourselves. And what we're also able to do to work with our numbers very well is that we can multiply them in any kind of way, as long as we multiply the entire row appropriately. For instance, we could use like one of the rows and we see an odd number there, and we don't want to work with odd numbers, because if we divide it by an even number, we're going to get some form of decimal. So what we could do is that we could multiply the entire row by 2, and then from there, as we continue to divide and get our Gaussian elimination, it'll be easier to work with so that we don't make a mistake when we're working with decimals.
I think there's a question.
Well, sorry.
Can you look at page 219, just 2 back?
219. Yeah, go ahead.
This is kind of a question for Dr. Kaswani. Like when we're doing our exercises, our programming homework, that n equals length of v, and then they plug in n for the for n range n. Can we just write like, oh, the number of equations 4, and then write a comment, oh, this is the number of equations that we have inputted for this one? Can we just write that, or do we have to write the n equals?
Well, this is just helpful. I mean, you don't have to write that. If you know how long your array is, it's perfectly fine. But you don't always.
Like it's really long.
Right? Like let's say you're not given A with all these values. Let's say someone hands you an n by n matrix. This would be how you find out how long it is.
So then we have next, if we go into LU decomposition. So LU, that's referring to the lower bound or upper bound. This is what we're talking about with our matrices, where we create that little staircase. So suppose that we want to create our such values that we want to solve for. In computational, it's harder for computers to make it understand our Gaussian elimination like how we would do on paper, because it's just we're trying to tell rocks to do something, but we would have to do it so precisely. So we have to figure out another method for us to approach solving these kind of matrices in these forms. So what we do is that we work with LU decomposition. And so you notice right here where we have such numbers, right? So we want to work column by column of eliminating them so that we have our one in the respective part of the matrix itself. And then we subtract it, and we also multiply by the inverse of the assigned value that it begins with in that specific position, right? Because we know that if, like, let's say in the our point A00 was 5, if we do 5 divided by 5, we know we'll get 1. So that's why we divided by the inverse from there. So also, because we're working in computational, we like to begin our assigned variables with 0. Typically, we would say A1, A2, A3, A4, but since we're working with rocks, then we'll begin with 0. So we say A0, A1, A2, A3, and continuously forward up until AN. So here we have what we call the matrix that we're going to be applying to, the lower bound 0. So because we say L0, this is referring to this part of the column. And then as we continue forward, you'll notice how we'll go down until we assign every placement of 1. So we work with L0, L1, L2, L3, and here's how we define it in such a variable form. So we have a matrix multiplied by x, the x being the variables that are assigned. It's equal to a vector of numbers. So when we gather our lower bounds, L3, L2, L1, L0, we can set it equal to each other, because if we know that they're equal, we can cancel it out, and we know that's how our methodology works. And this is our definition of our lower bound and upper bound. So we know that lower bound, it'll be the inverses of this work. So L0 to -1 and so forth. And the upper bound, it's just L straight up. The reason why is because our lower bound, we are focusing on getting the zeros completely down on the bottom left corner, or the upper bound on the top right. Ooh. And then this is just more continuous examples of how we use lower bound and upper bound. So then there's the next part I wanted to get to. Oh, and here's our formulaic way of viewing how each of our decomposition works. So as I referred to earlier, we have this staircase-like thing. So one way to view our values that we solve for, we use our v values. So the v values are vector. So we assign our vector components y0, y1, y2, and so forth. And we divide it by our value of L. I'm still not as good as explaining it. I wish I could understand it more better on how to explain how these matrices kind of work and translate. So I apologize if I'm not explaining it too well on that part.
Yeah, I think you're about to show the punchline on the next page. I think that's probably the most important part.
Yeah. So I think it was, it's this one.
Oh, no,
This one.
right there. That's
Oh,
the
right.
only, that's the only thing that you really need to learn in this segment.
Yeah. So with these, we could also use our NumPy package. So we can import linear algebra, or excuse me, from NumPy linear algebra, we can import solve. So what we do is that we assign our matrix and our vector, and we have to solve for the variables. So this is how one way to utilize these tools that we already understand and have used in the past, such as importing packages. This is another useful tool that'll help us with matrices and so forth. And then now we have calculating the inverse of a matrix. So when we calculate the inverse of a matrix, what we want to do is that we understand that x is just a vector and v is a vector. Here, to calculate our inverse of the matrix, we are going to transform x into some sort of a matrix and v into a matrix as well. Although it's not necessarily traditional that us physicists work with creating an inverse in matrices just like that. So there's not too much to go into detail, but a useful tool that I just mentioned before is, once again, if we use the NumPy package of linear algebra, we could import the inverse operation, and then we show our inverse of A. And then we have tridiagonal and banded matrices. So what this is that it's a matrix where there's kind of like a pattern going on. You notice how here it's a diagonal matrix, and what they say diagonal is because there's nothing going on here and there's nothing going on here. One prime example of such a matrix is happening is looking at a kinematic equation. So right here we have mass times acceleration, right? And we equal to the spring constant and the length of the object plus any other forces applied. And when we continue forward with it, if we were to write out this kind of equation, it would just look simply like that. And what happens is that when we apply such a distance, there is an acceleration going forth, and it'll progressively increase, but it's not going to be a uniform large matrix. It's going to be zeros in the lower bound and zeros in the upper bound, because it's just a progressive oscillation that's going on. So this is an example where we view this kind of tridiagonal output, and this could continue on forever. So we just continue till we say to the nth number as well.
Is this code the LU decomposition method, or is it something? Is it part of the tridiagonal and
The-
banded matrix?
This is associating with the tridiagonals. Right here.
And notice here that this performed the Gaussian elimination, and then you just back associate. You can do this at home, or you can do what David said earlier, you can just use the solve.
Yep.
Which one's easier? Oh, yeah, it's one line. Which one do you need to understand? Part of it, right? You need to know how the pig works before you make bacon.
So these tridiagonal or banded systems is very common in computational physics, especially if we're trying to calculate some sort of experiment that happens in the real world. So this is one of these ideas that is very useful to begin understanding and incorporating it into such code.
Can we pause for a second?
Yes.
So let's ask the question. Can you go back up one more?
Yes.
One more. There's a picture here of little masses, and they're combined by springs. What is this an approximation to in real life? The lattice of what? This is, you're overthinking it already. The lattice, just for folks who maybe don't know what a lattice is. What?
Like an atomic structure.
Of atoms, right? So it's a solid object. And so these atoms can move left and right. And as they move away from their central position, they encounter only their nearest neighbor. So the force, can you go down one?
Sure. Wait.
Almost there. So the force is only on its nearest neighbor. Right, so this is its compression and its neighbor's compression. This one, its nearest neighbor's to the left, its own compression, and the one to the right. Right, so the relative position. And that's how metals work. So if you want to do material science and you want to do computational material science, this is where you start. Figure out.
You tell me only metals have the lattice structure, like resembles springs, only metals do this?
No, not at all. I just said the word metal, but I didn't say only metals. In fact, everything has a metal structure.
Okay.
Everything has a lattice structure if it's solid, right?
Okay.
Is it as regular? Probably not. What's really interesting about things like wood is there certainly is a lattice structure, but they're long chain polymers because they're grown, right? And they fold and they bend and they wrap all around each other, right? As opposed to copper, which is like just rows and rows of beautiful grids. Right? Or if you take something like bismuth and you cool it, you can actually see the structure, crystal structure, right? But you don't have wood crystals.
Wait, I can see a crystal structure of business.
Oh yeah, we'll do that up. Don't look it up right now. Look, David, finish. Everything more, David?
No, it just goes into 6.2, so I'm all done.
Oh, perfect. Hey, okay, anyone have another question for David? All right, round of applause. Okay, folks. So let's do two things. We're reading the books, right? We're coming to class prepared. Okay. So that means that what we're going to try and do is we're going to try and understand a lot of really, really complicated linear algebra that you're not going to have to hold on to. Okay, so I'm trying to be honest with you. Understanding the linear algebra is not the most important part here. Understanding how we develop the algorithm is. So in fact, if you don't track the linear algebra, I'll give you a pass on that. But if you don't understand how the algorithm works, I can't, right? So if you found yourself being like, how do these lines go into each other? You know, take a step back, make sure you understand how the matrix of multiplication works. But after you've done that, kind of look at it from a little bit higher, right? Don't look at the line by line and try to get every single one correct. Try to understand what is the purpose of what they're doing with each of the decompositions, right? Okay. And then once you've fully understood that, you just import from NumPy. And it feels like you wasted everything. Yeah.
So if we're assessed on this and you ask us like about this section, then for an exercise, then we should be able to explain how to do that. So,
No. Every algorithm that you'll find to solve linear algebra has been made better and faster by someone who understands the code and the algorithm much better than you, and way, 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 way better than me. There are folks who, you know, their whole thing is okay, I'm going to build a better solver. And it's like building the better mousetrap, because every single like line, every single like exclamation point, comma, whatever it is they have in their code, when you're thinking about doing thousands or millions of calculations at once, like is sometimes necessary for linear algebra, time is of the essence. So they have optimized these things, right, to basically as good as you're going to get. So when we create one in class, it's clunky, it's ugly, but we do it because we want to understand how it works. Do you need to now then have that memorized so that you intrinsically understand how they work? No. But do you need to understand sort of the broad framework so that when you use the one that you find online, you can understand it? Yes. Right? But I don't expect you to go in and be like, well, step A in the algorithm is blank. Step B is, I expect you to be like, oh, if we want to solve this type of problem, we use this type of thing, right? Okay. Okay. So I think that the best way to start here, there's lots of problems. There's lots of really fun problems we can do. I think which way is it? Yeah, here. I think this is the one that I like to have folks start with in class, 6.1. This is a circuit of resistors. Now, what did I actually put here? Oh yeah, so I'm just an idiot. Okay, so let's just move this. Let's cut that. We'll do 6.1. Yeah.
I'm sorry, I was still doing 9.5.
No, we're not doing 9.5 at all. Did we do 9.5? Ever? Oh shit. Okay, well, let's make it homework. Okay. What?
Get that guy.
Get that guy. Okay, we're gonna do 6. We'll do 9.5 and we'll do a couple problems from 6. How about that? Don't say it like that. Okay, so 6.3, or sorry, 6.1 gives you this one. And this is good because it kind of gives you an introduction to solving systems of equations. What do we mean by systems of equations, right? We said it a little bit at the beginning. You have some matrix, you have some group, but I do want you to go from writing out the equations to creating that matrix. And I want you to be able to go back and forth between the two. Because once you've seen that, then you really get into, and I guess this will really matter the most for someone like Will. So Will is doing a coupled set of pendulums for his project, right? So here, imagine you want to solve all of these at once. That's a coupled systems of equations, right? Because all of these terms, they're all going to have these individual pieces that you need to figure out the simultaneous solution to it, right? So this is a really good example. If you want to solve anything that's not just a single particle moving, you'll need linear algebra. Now, we've done in the ODEs and the PDEs, we've done examples of how you have a coupled second order, or yeah, a second order equation. You'll break it into two coupled first order equations. You've done that maybe with one particle or even two particles. Now you can imagine I could do that with 10 particles, and I could use this type of solver to use RK4 at every step, right? Okay. So we're going to just keep trying to tie together different techniques. And if you feel like, hey, I didn't really understand that technique fully, like let's say you didn't quite get the Poisson equation, or you're still having trouble with RK4 or something like that, let me know, because we're just going to keep using them in different contexts. And so I don't want you to feel behind. Anyone here not tell me what they're doing for their final project? Well, we had a conversation today. Anyone else? Okay. Everyone started looking at it? They all definitely didn't just take the break and then go to the beach the whole time. Okay. We don't even go to the beach. Okay. Cool. Then let's get into groups. If there is an odd person who wants to jump on the Zoom with Trinity, I'm sure that she would appreciate it. Is that you?
So
What?
I'm gonna yell at her to a computer.
Well, I mean, put in your Zoom, AirPods. You don't have AirPods? Okay, there you go. You guys want to share ear holes. Okay, anything else before we get started? Okay, let me stop the recording then.